As a next aim, we want to compute inverses of matrices explicitly. And we will also do so by elementary row operations and by really doing explicit calculations. But before doing so, I want to establish some general properties of these elementary row operations. Namely, it turns out that each elementary row operation can be described as a matrix product with another matrix. Okay, by this I mean the following. Let us formulate this again as this hybrid of theorem and definition. 860. So assume we have an arbitrary m by n matrix where m and n are natural numbers, a in m by n k. Let again Im denote the elementary matrix. So Im, the identity matrix. Whoops. So the matrix which has 1 on the diagonal and 0 everywhere else. In particular, it's a quadratic matrix. Then, so let this be the identity matrix. Now, if T is an elementary row operation, then you can compute the following. So T of A is given by some matrix times A. And let's think for a moment. So we have an m by n matrix before, and the result must be an m by n matrix again. So if I had now an audience, I would ask, what form must this matrix be? This which I multiply it in order to get an m by n matrix again. How many rows and columns must it have? So maybe think about this a little. So this is m by n. This is m by n. The result should be m by n. Now this means the first thing here must be an m by m matrix. So this must have m many columns because this has m many rows. Otherwise the product wouldn't be well defined. But afterwards, this should again have m rows. So the number of rows of the first factor should be m. So we get m by m. And this m by m matrix that fits in here is T of the identity matrix, actually. So if we apply this swapping of rows or adding or something, we can just apply this to the identity matrix and then do this matrix multiplication. Now, first of all, and this is the definition part of it. So this is a theorem, and the definition part is a matrix of this form, of the form T of Im, where T is an elementary row operation. Let me abbreviate this again. This is the E row of the day. This is an ERO. Is called an elementary matrix. This is the definition part of this theorem and definition. Okay, this is the notion of elementary matrix. So I will skip the proof of this. Because this is kind of really explicit computation, proof skipped. It's not very insightful. It's really, if you just do the computations and really do the definition of the matrix product and compute a lot, then you see that this precisely does what it does. And if you want to understand these things a little better, just try to compute these products on your own. And to help you a little bit, I want to give first the explicit forms of these elementary matrices for the 3 types of elementary row operations that we had. So explicit forms of elementary matrices. And this is now quite some tedious work. Okay, first of all, so the first thing was swapping 2 rows. Okay, so we had this operations Sij, and for this we had I and j row indices, so between 1 and m, and we had always assumed that I is smaller than or equal to j. Then, So the corresponding matrix, which I will call Pij, so this is now an M by M matrix with entries in K. So Pij is by definition Sij of the identity matrix. So what do we get if we swap the ith and the jth row of the identity matrix? It's quite obvious, but let me write this down. And for this, let me do again the fast forward mode. Okay, slight interruption. So we have ones on the diagonal, and I'm using the convention here now that everything I haven't written down is filled by 0. So I don't write all the entries in there. I have a bit more detailed form in the lecture notes, but everywhere where there's no number written, there's a 0. So what have we done? So so this is the diagonal here of the identity matrix, and assume now here we have the ith row, and here we have the jth row. Now, if we have swapped these two rows, originally here were just ones on the diagonal, so if we have swapped them, this just means that here we have this one which was up there is now here in the jth row, and this, the same part, the one that was here, has been moved to the ith row. So here we have all 1, 1, 1, 1, 1, and just on this one position we have this situation that these are here in the same row. This is poorly drawn, I'm sorry about that. But here we have this and, sorry. Okay, maybe like that. So, and here this is the ith column, since this is the diagonal, and this is the jth column. So just take these two ones and move them to the other side, and the rest stays as it is. So this is the one form of elementary matrices. And again, everything that I haven't filled into is filled by a 0. Okay, now for the second type of elementary matrices, so elementary row operations, we had multiplication of rows by constants. That's probably the easiest. So multiplying a row by some lambda. So for this purpose, I is some row index. Lambda is in K but not 0. So then, if we take Qi lambda, which is again an M by M matrix, if we take Qi lambda to be, and I called these multiplications M, so M lambda I of the identity matrix. So what does this look like? And this I can do easily. So we have ones on the diagonal. And just in the ith row, we just multiply everything by lambda, but since almost everything is 0, the only thing that's changing is this 1, and this 1 is becoming a lambda. So here we get lambda, then we get 1s, and we get 1s, and the rest is just covered by zeros. So yeah, let me do like this. So here's everything here is 0. Okay, so this is the second type of elementary matrices. Now the most sophisticated maybe is the third type. So see, this was adding the lambda-fold multiple of the jth row to the ith row. So here I call the matrices R lambda I j. So again, M by M matrices. R I j lambda is defined to be the operation E lambda I j performed on the identity matrix IM, which now looks as follows. And another fast forward, please.
So take this matrix, we have 1, 1, 1, so there's a J, here's the ith row, like this, 1, 1, okay, maybe like this.
Okay, here we are. So now we do some little difference. So we first take so this is now the identity matrix itself. Now if we have the ith row, let's say it's this one here, so where this one is there. So we now have to take the lambda fold multiple of the jth row, and let's say j is somewhere over here. Let's say this is the jth column. So if we then add so this is somehow somewhere here maybe. So if we now take lambda times this row and add it to this one, the only thing that's changing is now that here we get some lambda in this jth column. So this means here we have another lambda. So lambda is in position I, comma, j. So just the identity everywhere with some lambda here in this particular spot. Okay, now this is the third type of elementary matrices, and this is what they look like explicitly. So we've seen them once. Now, since we want to go for invertible matrices now, we have recall that every invertible matrix is necessarily a quadratic matrix. So it has to have the same number of rows as it has as columns. And this is now what we're going to focus on. And now the first thing we're going to do is to take a look at the invertibility of a map in terms of the row echelon form, and take a look at what this row echelon form then needs to look like, as we shall see after I erased. And another hybrid of theorem and definition. So theorem definition 861. So let n be a natural number and A be a quadratic matrix with so quadratic n by n matrix, m n by n k. Then, now first the theorem part of this. A is invertible if and only if A is row equivalent to a matrix of the form given as follows. So we have B11, B12, and so on to B1n. But now we have first a 0 and then B22 going to B2n, and maybe at another B23. In the next row we have 2 zeros in front, and then B33 and so on to B3n, and so with each one becomes 1 0 more until at the end we have only 0, 0, 0 and so on, and then Bnn. Yes, like this. Okay. In particular, i.e. such that, so everything below the diagonal, so here below the diagonal is 0. This means Bij is 0 if the row index is bigger than the column index. So I is strictly bigger than j, and such that, this is not obvious from this, the elements on the diagonal, which are all of the form Bii, they are non-zero for all I between 1 and n. Okay, and this was the theorem part. Now the definition part. Such a matrix is called upper triangular, right? Because there's a triangle of entries in there which is possibly non-zero. Upper triangular. Okay, now proof. This matrix I call B. So capital B. Now, first the easier direction. So assume A is row equivalent to a matrix of the form this. So here, obviously, because all the diagonal elements are non-zero, by the same argument as I used in the row echelon form, here you can see that the rank of this must be n. So rank B is equal to n. But since the two are row equivalent by assumption, it follows from theorem 853 that rank rank A is also equal to n. But this means that the rank of the map induced, or it's even equivalent to this, that the rank of FA is equal to n. And this is the induced map, which is now a linear map from Kn to Kn. And the rank of this is n, so it's everything. So this means Fa from Kn to Kn is surjective. And we've seen that linear map between vector spaces of the same dimension. I haven't written down the precise statement where we had this yet. It was a theorem. If you have two finite dimensional vector spaces of the same dimension, a linear map is surjective if and only if it's injective, if and only if it's an isomorphism. So this means Fa is an isomorphism, and this of course means that A is invertible. Okay, now for the other direction. So assume A is invertible. So if A is invertible, then it follows by the same argument in reverse here. So going from here to there, this was all equivalences. So yeah, let's do it maybe once explicitly. So if A is invertible, then the rank of A is n. So this means, so we've seen that by Theorem 857, A is row equivalent to a matrix in row echelon form. Row equivalent to a matrix B, so whose entries I will call B I J, in row echelon form. So, but what does this mean at this moment? Since since the rank is equal to n, this means so by Theorem 853 again, since they are row equivalent, now just other way around, the rank of B is n. So this means we have no vanishing lines, so this means in every no vanishing rows of the matrix, which means that in every row of the matrix we have a pivot. So this means, so to formulate these pivots, we have numbers j1, j to jn from 1 to n, so column indices, we have n columns, such that Bij is, Bij is a pivot for all I between 1 and n. But this means, in particular, so because of the pivot properties, we need to have that J1 is strictly smaller than the J2 and so on to Jn. So we have n numbers which are not the same, but which are really increasing, and we know that they are between 1 and n. So 1 to n, these are n different numbers, and we have n different numbers between them. So there's not that many possibilities because we have this strictly increasing condition. So the only possibility where this can happen is that this is 1, this is 2, and so on and so on, and so this is n. There's no further space left. So this means Ji is equal to I for all I between 1 and n. And so this means Bii is a pivot for all I in 1 to n. And if you take a look at the definition of a pivot, this is precisely this form. It becomes upper triangular. This is the row echelon form of this is a matrix in row echelon form where all the pivots are precisely the elements on the diagonal. So this means B is upper triangular. And this is what we wanted to show. So we got that. So, okay. So much for that. So we've seen matrix is invertible if we have this beautiful form, a row echelon form matrix, which is row equivalent to the matrix itself. Now, so to really use this later on, we will use this then to compute the inverse, this approach here, because we know that if we, by the Gaussian elimination method, if we have a matrix, this upper triangular matrix, which is the row echelon form, this is something we can compute explicitly. This is what we did in the previous subsection. We computed a row echelon form of a given matrix and then made the conclusion for the rank. But here we can always compute such a matrix, so by explicit methods, and we will do so later. Now, to further proceed, let me make one observation. Namely, so we can form this, transform a matrix into this form by elementary row operations, which means by products with elementary matrices. Now, there's one useful property of elementary matrices that that is then crucial that we can use in the proof then to establish a nice property, namely all elementary matrices. If you take a look at them, it's maybe not that obvious, but all elementary matrices are invertible. This is something you can compute. So, first of all, each elementary matrix is invertible. And its inverse is again an elementary matrix. Again, elementary. Elementary, dear Watson. Yes, this is so. In particular, or more precisely, we can also write down the inverses for all m in n. So, and we consider the elementary matrices as m by m matrix. So, first of all, let's take a look, and this is nothing I will prove, but I will just discuss the idea here now and how we see this. This is the inverse, and I will now give explicit formulas for the inverse, and you are, of course, cordially invited to really compute this in detail. So really to compute matrix products, and then this is really good if you want to understand matrix products in detail and feel a bit insecure with them still. Now, Pij, the matrix which swaps the ith and the jth row. What is the inverse of this? So if we kind of flipped the ith and the jth row, what do we need to do to get the original matrix back again? So we just flip again. If you change twice, you didn't change anything, because just flipping, which means the inverse of Pij is indeed Pij itself. So for all I smaller than or equal to j and both numbers in 1 to n. Bit sloppy with notation, but that's fine. Okay, B, the multiplication. So if I take the matrix which multiplies the ith row by lambda, what do I need to do to get back to the original matrix? Well, I have to multiply the ith. So if I want to invert this, I have to multiply the ith row by the reciproc. So just qi multiplied with 1 over lambda. Lambda is by construction non-zero, so this is fine. For all I between 1 and n, and lambda in k without 0. So this is really easy to see, but you could also do a formal computation if you want. And finally, okay, so if I have added the lambda fold of the jth row of a matrix to the ith row of a matrix and have done this effect, what would be the inverse of this? Okay, if I would have an audience, I would now ask, we would have a multiple of the jth row again to kind of undo the damage we did, but we just need to multiply with the right number, because we just can multiply, so again, add a multiple of the jth row to the ith row, but now we take minus lambda. So because the one thing adds a lambda in the one component, this adds a minus lambda in the one component, and obviously lambda minus lambda is 0, so the damage is undone. So this for all ij between 1 and n, and lambda in k. And as I said, I will not do a formal proof of this statement. So A little sketch of proof or a method of this is in the lecture notes. Okay, now, so why did I do this? The reason is the following beautiful theorem, Theorem 863, and this will now be the key observation, how we relate invertibility of a matrix with elementary matrices, and this is the property that we will use to give this will then indicate of how we can construct the inverse of a given matrix explicitly. Namely, let M and N, every invertible matrix, M by M matrix, is given as a product of finitely many elementary matrices. So any invertible matrix, no matter how complicated it is, can somehow, so to say, be decomposed into factors such that each factor is very simple. Right? These in elementary matrices are really simple matrices. Many entries are vanishing, which makes many computations simple. Yeah, this is kind of what we can do. We can really do this and decompose this into simple factors. And this property, this is kind of the theoretical guarantee for some method that we will then use to give the inverse, and this theorem kind of guarantees that this method works, and this is always doable. Okay, let me erase, and then I'll show you the proof and how to see this and how to obtain then the inverse of a matrix. We have seen in the previous theorem that we can transform an invertible matrix into an upper triangular matrix by a finite number of elementary row operations. So since this is given by multiplication with elementary matrices, this means we can multiply with finitely many elementary matrices to get our upper triangular matrix. So to formalize this by theorem 861, there are finitely many matrices, so formally there is some finite number R in N, and elementary matrices E1 to ER, such that the product of A with E1 times E2 times and so on to ER, if we call this result B, so we can do this such that this is upper triangular. Okay, and we again call the entries of B small b ij. So just as a little reminder, so B is of the form, let me just scribble this here in the corner, B11, B22, and so on to Bnn. So everything here is 0. So, and everything here is terra incognita. So these are just some numbers and we don't know what they are. B12 and so on to B1n, B2n, and so on. So this is where we are. Now the idea is now, what we now want to perform is we want to transform this into the identity matrix by elementary row operations. And it turns out that this is really possible. So transform B into the identity matrix IM by elementary row operations. Okay, namely, this is now formally a bit complicated, a bit messy. So basically, it's a similar procedure to what we did to get from our original matrix to this row echelon scheme. Now we saw maybe, we want to do this column by column. So first of all, we know that in the last row, there's only this one number missing. So we can add the sufficient multiple of this row to each of the other rows to make this coefficient here disappear. So we just take a multiple of this row, add it to each of them, and we just need to choose the right multiple. And the good thing is this is non-zero, this is what we know. So we can really play around with this and then make all these coefficients disappear. So afterwards, we can then take the second to last row, which is now also where the last coefficient is gone, which is just 0. So there's only one, this coefficient bn minus 1, bn minus 1 would be remaining. And we can use this then in the same procedure and kill every elements in the column above this element and do this column by column by column until we have erased everything. And then we have a matrix where there's only entries on the diagonal which are non-zero. And when we are at this point, let us consider again what we do. So let's first get there. So formally, first of all, for each, let us first kill this last column. Oh, sorry, I have, this is now an m. Somehow I'm mixing up my m's and n's. Now I'm sorry, here I'm considering m by n matrices, so this is now m and not n. Reminder, everything is quadratic here. This is important. Okay, so for each, so we need to kill the mth column here. So for each I between 1 and m minus 1, we consider the following coefficient. Lambda im is defined to be minus, and now we need the right number. We need to multiply it with bmm to achieve this coefficient here, so to neutralize this coefficient when we add it. So we need to take minus bim over bmm. Okay, and then if we got this number, add the lambda I-fold multiple of the mth row to the ith row for each I, and we call the result Cm. And now, as these are all elementary row operations, this is again obtained by products of elementary matrices. So each of these steps is obtained by just multiplying with some particular elementary matrix. And to do this in detail, so we had the original matrix M. So to kill the coefficient which was here in the mth column and row m minus 1, so we needed to apply the lambda m minus 1 fold multiple m minus 1 m. So this is the operation which adds the lambda m minus 1 fold multiple of m to the of the mth row to the m minus first row. So and so on, and let me write it like this. So the first, to kill the first, we need lambda 1 m, then r lambda 2 m, and so on. And this is again a product of, so we know M is a product of elementary matrices with A. These are all elementary matrices, so we're just adding further and further and further elementary matrices. Okay, now Cm has now the property, so the only, let me write it up there. So now the only non-zero entry in the mth column of Cm is in position mm, so really the bottom in position mm. Okay, now we've cleared the mth column, and now we can basically forget about the mth column and the mth row and take this m by m m minus 1 by m minus 1 matrix, which is remaining, and do the same thing again. So let me abbreviate this and do this formally. So for each column we need to do this. That k in between 2 and m, and let, so now do this recursively, let ck be given. And now we want to produce a matrix called ck minus 1. So we start with Cm, produce Cm minus 1, Cm minus 2, and so on. And for each matrix ck, we will have the property that everything in the kth column and everything right of the kth column is cleared of cleared of entries which are not on the diagonal. So formally, let me do this. Okay, now we're coming to index hell. Let me call the coefficient ckij. So k as this k and ij be the index. So for each I between 1 and k minus 1, in this case, 1, k minus 1, put lambda I k to be, and now welcome ugly indices, c I k k divided by c k k k. Beautiful, isn't it? Sorry. But there's, I found no other way to handle this, but we have these triple indices. Lovely. Okay, so this is the right number that we need to add then the lambda I k fold multiple of the kth row, which is now, after this procedure, a row where kind of everything right of this kth entry is gone. So this row is only having one non-zero entry on the diagonal. So multiple of the kth row to the ith row. And we finally then define the matrix Ck minus 1 to be the matrix that we obtain after we did all this. This means this is again a product by of elementary matrices. We have first the lambda 1 fold multiple of the kth row to the first row, then the lambda, 1k, lambda 2k fold multiple of the kth row to the second row, and so on until lambda k minus 1 k minus 1 k times ck, and no, I've not gone crazy. This is really what you need with the indices here. But this is just, if you get the idea, the details are not that important, but you need to understand what's happening here. So this is just every time the product with the correct elementary matrix. So if we do this, and do this again and again and again, we obtain following this procedure. We finally obtain a matrix called C1. So this is C1 of the following form. There, the matrix was upper triangular before, and so it is later. And then we've cleared all unnecessary entries, basically. And so this means, in the end, we only have entries on the diagonal left. And let me call them D11, D22, and so on until dnn, and everything else is 0. Okay, such a matrix is also called a diagonal matrix for obvious reasons. But what you also get from this procedure is that all the diagonal entries are really non-zero for all I in 1 to m. Oh, I've again messed up this. This is mm. Oh, did I? No, here the m's are correct, okay. So, dmm. Okay, now we want to transform this into the identity matrix, and this is obvious how to do this. Since these are all non-zero, we just have to multiply each row with the reciprocal of the entry in there, because all the zeros stay as they are. Oh, dots missing. Stay as they are, and so we just need to get a 1 on the diagonal here. So then it turns out that if we multiply the first row with 1 over d1, d11, then the second row with 1 over d22, and so on, until we multiply the, wrong name. I didn't call it, M was the operation, the matrices I called Q. So just not to confuse, I want to write this as matrices here. And then finally 1 over dmm in the nth row. So if I do all these multiplications and apply them to C1, I will get the identity matrix. Now, so C1 was originally given as a product of the original matrix A that we started with a lot of elementary matrices, but they are all elementary matrices. Which means, now, there exists a finite number of elementary matrices. So let's call this number then K. There exists K and N, and B1 to Bk elementary matrices. So just need to combine all these procedures and do them one after another. So this K might be huge. possibly. Sorry. So we need to do these operations again and again and again. So we get a lot of elementary matrices. And finally, we've shown that we can find such elementary matrices such that B1, B2, and so on, times Bk times the original matrix A, in the end gives us the identity matrix. Okay, what does this help? This means, just by definition of the inverse matrix, this means that this matrix must be the inverse here. So, in other words, what happens here must be since, each Bk is invertible. So we've seen that the invertible matrices form a group, so the product of all these matrices is invertible. And since the inverse is unique, this matrix here must be the inverse. So since B1 to Bk is invertible, so the product here, this is what we showed before. It was by theorem, what was number 862. And we know the inverses are unique. So this means A must be, A is the inverse of B1 to Bk. But we know that the inverse and the matrix product, there we've seen that the inverse of a product is the product of the inverses, but with order reversed. So by theorem, which was that? Theorem 815b, this is the same, the inverse of this product, as bk to the minus 1 times bk minus 1 to the minus 1 and so on, times b2 to the minus 1 by times b1 to the minus 1. And we've seen the inverse of each elementary matrix, since these are all elementary matrices, are again elementary. So this is a product of elementary matrices, which is a product of elementary matrices by theorem 862 again. Okay, so we're done. We wanted to show that A is a product of elementary matrices, and this was a lot of work, but in the end we have this long product here, which is the product of elementary matrices. Okay, now, this is now enough we have now enough information if we take this procedure, so really the proof of this theorem, and not the theorem itself, but this, you really need to understand this method that we did by clearing out the columns and so on. And we can now really use this procedure to compute the inverse of a matrix. And since this is now this, I want to have enough space for this and also to compute an example, let me erase at this point and then I will show you how. So finally, how do we compute the inverse of a given invertible m by m matrix? Now the key is basically are the observations we made along the way. So it's basically the friends we made along the way. So we have seen that if we start with a given invertible m by m matrix, we can first make it up a triangular by elementary row operations, and then turn it into the identity matrix by elementary row operations. So apply a sequence of elementary row operations to transform A into the identity matrix IM. Now, what we do, we apply the same operations, the same elementary row operations to IM, call the result not the result, the product of the corresponding matrices, of the elementary matrices. Sorry, tiny mistake. We apply these operations to IM, we call the result B. Okay, and then, so since B is the product of those elementary matrices. Since we started with the identity, we just have purely these elementary matrices that correspond to these operations we apply, of those elementary matrices that transform B into IM. It follows, not B, to transform A into IM. This is precisely what the inverse does. It follows that the inverse matrix of A is B. So this is indeed the inverse matrix that we can get in this way. Right? So the theorem before is kind of the theoretical insurance or the guarantee that this procedure works. And this is how we can really explicitly determine this. And to make it clear to you that this is really, that we can really get the result with this, I will, of course, do an example. Okay. Example 864. Okay, we consider, again, a 3 by 3 matrix with real entries, so I don't want to be too brutal with you. Don't call it A, so it's, A is the matrix which has the following entries: 0, 1, minus 4, 1, 2, minus 1, 1, 1, 2. So this is a real 3 by 3 matrix. And yeah, here one checks, and this is non-obvious, but that this is really invertible since the rows of this matrix are linearly independent. So one checks that A is invertible. In the next chapter we will learn another criterion of how to check if a matrix is invertible, which is often a bit easier. Okay, one check this is indeed invertible, and now we apply this procedure that I just mentioned. So first apply Gaussian elimination, so to turn this into an upper triangular matrix. And we do the steps we get to make this upper triangular and perform the same to the identity matrix. This time M is 3, so we need to study the matrices 0, 1, minus 4, 1, 2, minus 1, and 1, 1, 2. And just we do this, it's like with bookkeeping, where you always have two entries where you kind of enter the numbers, so to say. We do this on the one side, and on the other side we do the same stuff to the identity matrix, which is of course given like as this matrix. Okay, now, so let's think about what do we need to do to have Gauss elimination. So first of all, we have to bring the first, so the lowest non-vanishing column index, which has non-vanishing entry, this should be in the first row in order to make this pivoting method doable. So here we see, here's a 0, below there's not, so this is not what we want. So what we do instead now is we can either swap these two rows or these two rows, and I decide to make this, so you can just do it other way. So we apply S12, the swap of the first and the second row, which then gives, so 1, 2, minus 1 is now the new first row, and the second row is 0, 1, minus 4, and the third row remains as it is, 1, 1, 2. And now we do the same thing to this matrix. So here then we swap these two, so we get 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay, now as a next step we have to make this one the pivot element. So here it's easy to see what to do. We need to multiply this by minus 1 and add this to the third row. So as elementary row operation, we have written this as E minus 1 and now 3, 1. So adding minus 1 times the first row to the third row. So this becomes, okay, this is now a bit not very good with the blackboards. So minus 1 times this to the third row. So first of all, the first column becomes 1, 0, 0. So the second column, so 2, 1 stays as it is, and then we add minus 2 in the third row, and so 1 minus 2 gives minus 1, which, and in the third column here, so we have minus 1 times this is plus 1, added to the 2 there is a 3 in the end, and the other two stay as they were, it's -1, -4. Okay, and again, we have to do the same thing on the other side. So we have to apply the same step to the result at the inverse matrix. Oh, maybe I can use the blackboard a bit more efficiently. So we again have to apply E-1, 3, 1. And so in this setting, this becomes, so the first two rows, of course, remain unchanged. So 0, 1, 0, 1, 0, 0. And now -1 times the first row to the third row, this becomes 0, -1, 1. Okay, so what next? So this one is a pivot, and now we have to make the second one a pivot. And here it's now, because the numbers really work well, we just have to add this row to this row. So this means we have to take the one-fold multiple, so to say, of the second row to the third row, which is this. So this means here we get 1, 2, -1, 0, 1, -4. And here it's 0, 0, and then add this to this. So this is -1. Okay, and now do the same steps here. So E1, 3, 2. So this means we just get 0, 1, 0, 1, 0, 0, and now 1, -1, 1. Okay, so much for that. Let me maybe erase this middle bar because I want to use the space a bit more. So now this is upper triangular, which is good news. Okay, so now we need to create this method of killing columns. So so apply method. Of course, if you have to do this yourself, you have to write this every time. Apply method from the proof of theorem 863. So, which means we need to kill the individual columns. So first of all, to do this, to make life easier, we just do an intermediate step. We multiply this third line by -1. So we just get a 1 there. So apply m -1, 3, which gives 1, 2, -1, 0, 1, -4, 0, 0, 1. And same on the other side. M -1, 3. So it's 0, 1, 0, 1, 0, 0, and -1, 1, -1. Okay, now here we see what we need to do next, how we can kill this column. So we need to do 4 times this row and add it to this row, which means we then get, so this would be E4, 2, 3, 4 times the third row to the second row, which gives 1, 2, -1, 0, 0, 0, 1, 0, and 0, 0, 1. And on the other side, we get so 0, 1, 0, and now 4 times this added to this, which means we get -3, 4, and -4 in the middle, and the rest stays as it is. Okay, now we got there. So we need to kill this one, obviously, so we just need to add the third row to the first row, which would be E1, 1, 3, which would then kill this, which gives 1, 2, -1, 1, 2, 0, 0, 1, 0, 0, 0, 1. And on the other side, we get E1, 1, 3, which gives, this one to this. So we get -1 to -1, -3, 4, -4, and -1, 1, -1. Okay, now, so next we need to kill this one here in the column. You see this is becoming a bit tedious. This one. This is the pivot which still remains to be killed. Sorry. So what we need to do is take this by minus 2 and add it to this row. So E minus 2 and then 1, 2. So then we get 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the identity. Hooray, this is where we wanted to go. And here we do the same, E minus 2, 1, 2, which gives, now it becomes a bit messier, so minus 2 times this added to this. So this is plus 6 to this gives 5. Here we get minus 8 plus 2 is minus 6, and here we get plus 8 minus 1 gives plus 7, minus 3, the rest stays as it is, minus 3, 4, minus 1, 1, minus 1. So this is our solution. This is the inverse, and unfortunately I don't have space here anymore to write the conclusion here. Maybe that we write it there, so forget about that for this. So here we've shown that the inverse matrix is indeed this strange matrix there. 5, minus 6, 7, minus 3, 4, minus 4, minus 1, 1, minus 1. Okay, this is the inverse of the matrix, where is it? There. Which is really non-obvious, because no one would have picked up these numbers 5, minus 6, 7. This is something you just, also if you're an expert or something, you don't look at this matrix and see the inverse or something. That's just not what happens. So this is the way of how to compute the inverse of a 3 by 3 matrix. And as you can imagine, if I would have given you now instead of a 3 by 3 matrix, a 5 by 5 matrix or something, this would be a lot of work. It's a bit tedious, but this is kind of the method, and you have to do always the same procedure again and again and again. Okay, now this is good news, because now we can really, if I give you a rectangle of numbers, you can, which is invertible, you can give me back a rectangle of numbers, so it can really compute stuff. If you want to check if you computed correctly, there's an easy way to prove this. Take the product of this with A and compute that the result is the identity. If not, then you somehow, somewhere on the long way, made a mistake. Okay, this is how we learn to invert a matrix, and now the next subsection will be about finding solutions of linear equations, systems of linear equation in a very general way. And it turns out that we don't need that much more theory, because we can really use a lot of things that we did along the way. Okay, let's continue with that.